In this section, we will discuss relative illumination, roll-off, and vignetting. In optical system design, relative illumination is the decrease in intensity as you move across the sensor. It can be characterized by a bright center and a relatively dimmer corner. This lens performance metric combines the effects of vignetting and illumination roll-off, both of which I will be discussing in this section. This RI, or relative illumination, is given as a percentage of illumination at any point on the sensor relative to the field position with maximum level of illumination. As an example, we can see this relative illumination curve or RI curve. It starts with 100% and decreases as we move along the sensor. This nice demonstration shows the effect of sensor size and f number on RI. As we know, lenses with lower f numbers are known as fast lenses, which essentially means the light throughput is higher here compared to lenses with high f numbers. As you can see here, the f1.4 lens here has an RI of 57% at the corner of a 2/3 inch sensor. For the same lens, RI is 72% at the corner of a 1/2 inch sensor. This implies that the relative illumination improves if you reduce the size of the sensor. This image here shows how illumination changes across the sensor at f1.4 for the 2/3 inch sensor. This practically shows the blue line here, but in a different way. If we look this comparison, we can see that relative illumination performance looks better for high f number or slower lenses. We will now discuss vignetting. Vignetting is characterized by a loss in relative illumination when light rays do not make it through the imaging system on their way to the sensor. Some of the rays essentially get clipped by the edges of individual optical elements. It's more commonly observed in lenses with low f numbers. If you think for a second, low f numbers mean high light throughput, and it becomes increasingly likely that some of these rays will not make it through all the elements in the system. As an example, you can see that in this f1.8 lens, the rays are getting clipped here and here, which causes vignetting. On the other hand, when you look at a slower lens, f4 lens, you can see that none of the rays are getting clipped, so there is no vignetting happening here. From this comparison, it's clear that the sizes of the optical elements are very important when vignetting needs to be considered. Another thing that I should mention is that sometimes vignetting is intentionally introduced in optical systems. It can be for a number of reasons. For example, vignetting can be intentionally introduced to block stray lights or to improve overall lens performance or even cut some cost. Now we will discuss roll-off. Illumination roll-off is the decrease in RI that is governed by radiometric laws, not by vignetting. Briefly, it scales as cosine to the power 4th of the chief ray angle in image space. As we know, maximum value of cosine is 1, which is when the angle theta is 0 degree. So what it implies is that as the angle increases, the cosine of theta will decrease. And when we take cosine to the power of 4, there will be quite a bit of loss in illumination. Take this imaging system as an example. The green and blue lines show corner and center chief ray bundles. Now let's see how the angle between these two affects the RI. For that, let's look at some numbers. With a theta of 5 degrees, RI is decreased by just 1.5%. But for 15 degrees, it jumps to 12.9%, and for 30 degrees, nearly half of the illumination is lost. In most applications, roll-off is not a big concern, but for some specific applications, they can become a major issue. For example, in imaging systems where short working distance and large field of view is needed. In those cases, roll-off can be corrected by designing imaging systems that are image space telecentric, which essentially means the angle of the chief rays will be 0 degree, which produces even illumination.